now going to start our next session. The session 1, carbon recycling and reduction. So it's an important area of active research around the world, as everybody has understood by now that we are trying to decarbonize in several ways that are available to us. So this is one very key aspect of our efforts. So the leader for the debate and the presentations is Dr. Fernando ACTIS. So he's going to take the lead.
Thank you, Rizwan. So we will start this very interesting session. The use of carbon goes back all the way to the beginning of iron making. This use was necessary by the fact that carbon is not only a very effective reductant, but more importantly, it lowers the melting temperature of iron and gives steel the strength it is known and used for. The efforts of decarbonization aim at lowering our reliance on the fossilized form of carbon. The industry has various examples of using the bioform of carbon, as well as keeping the carbon in a perpetual loop of multiple passes so that the reliance on fossilized forms become lower. The presentations in this session will outline these examples. So let me introduce to our first speaker, Mr. Basavaraj BOMMAN, manager of JFW Steel Limited. The title of his presentation is Use of Alternative Carbon Sources in Blast Furnace. Please.
Thank you. Good afternoon, everyone. Myself, Basavaraj BOMMAN. I am Deputy General Manager in JSW Steel, looking after sustainability and decarbonization journey initiative implementation in JSW Steel. With me, Mohan Raj, my colleague, he's working in blast furnace. Yeah. Can we have the slides?
You have to use this. Okay.
Yeah. I'm very happy to present you the deck with the esteemed guests gathered here. So the presentation is basically on the use of alternative carbon source in blast furnace and also in sintermaking in JSW Steel. Let me introduce about JSW Steel before going in details. JSW Steel is presently 28 million ton capacity, and it is having 5 integrated steel facilities across India and also 7 downstream facilities in India. And also we are present in the overseas. We have got facilities in USA, we have facilities in Italy, both put together having a capacity of 3 million ton. If you see the right side of the slide, which shows the growth journey of JSW Steel. JSW Steel started in FY99 with 0.8 million ton capacity with a Corex technology what we have started with. And we are very ambitious and aiming to achieve 50 million ton capacity production by FY30. Yeah, as for any business, the sustainability becomes the paramount focus area. For us, the Sustainable Development Goals, 17 parameters are the major paramount focus area. We are in line with the national and international framework, and along with, we are driving sustainability initiatives across all platforms, and also started reporting sustainability parameters in integrated reports. So I want to seek your attention on this slide, which shows the JSW's roadmap for decarbonization. We are targeting 48% CO2 reduction by the FY30. If I see, the graph shows two parts of this. One is whatever we have achieved till now. So the base year is 2005. From 2005 till now, we have reduced around 30% of CO2 reduction. From the challenge and journey begins now. The challenge is very high. So further onwards, we are planning to reduce around 18 to 20% of CO2. So by FY30, we are committed and published, we will be less than 2 ton of CO2 for producing 1 ton of crude steel, somewhere around 1.95. Though it is published, we have got an internal target much lesser than this. So the major levers for reducing the CO2 is, one is RE power, the second one is solid fuel reduction and gas injection in blast furnace, pellet burden and increasing pellet in blast furnace, scrap addition and waste heat recovery.
So in last slide, we have seen the short-term plan. So in this, we are seeing this decarbonization journey strategy for JSW Steel. We are working on the 4 different themes like fuel and energy recovery and energy and technology transformation and circularity. So in the long-term plan, we are planning like fuel rate optimization through hydrogen injection in blast furnace and syngas addition in blast furnace and hydrogen injection in DRI units. Coming to this energy recovery, we are planning this top gas recycling. In morning also we have seen the course 50. So this is also one of our the main concept, and this slag heat, waste heat recovery of the slag. And this energy transition, we are going to transform the technology of NCAMP and BF and implementation of CCUS across our manufacturing unit. And we are also working, and soon we are going to commission this scrap-based EAF facilities in our complex. So coming to the one of the major initiatives, so as of now we are operating 25 megawatt of integrated steel plant facilities, and this is solar based, and 600 megawatt of RE through wind we are going to commission very soon, and total by FY25 we will be 1000 megawatt RE power in the integrated steel plant facilities. And by 2030, we are going to phase out 100% phase out of thermal coal-based power production. So we'll be around 50% RE power in our circuit, and remaining 45% of gas-based power, and remaining 5 to 8% of from the grid we are going to use. So the next major initiative is green hydrogen. So we already had a foundation of 25 megawatt electrolyzer, so which capable to produce 5,000 nm cube of hydrogen. So in phase 1 and phase 2, we are going to make 20,000, and phase 3 we are going to make 125,000. This will fulfill our requirement of green steel production of DRI units. We are already running 2 million ton of DRI unit in a Vijayanagar location. And the third is the carbon capture. Already we have 100 ton TPD of carbon capturing plant. We are in the Salav unit. So it has a purity level of 99.5%. And this we are working on to scalable this production unit to all manufacturing locations. And we have tied up with, collaborated with suppliers to study the feasibility of various CCUS technology in our complex.
Let me tell how the decarbonization journey is going in JSW Steel. We have launched a program called SEED program. The SEED stands for Energy Emission and Decarbonization. This program we have launched in JSW Steel, Vijayanagar, and now it is horizontally deployed in Dolvi, Mumbai. So this program involves the bottom-up employees capturing the ideas for decarbonization and also energy conservation ideas. So we have identified more than 400 participants were there, and we have identified more than 200 initiatives. And these initiatives are being tracked and monitored in climate action centers. We have got 15 climate action centers in JSW Vijayanagar, where all the projects are being tracked and monitored every fortnightly. And also we have got 40 initiatives which we have implemented in last financial year. And there is a digital platform called Seed Emission Manager, where the CO2 generation and impact KPIs which are impacting for the CO2 are being tracked in this emission manager dashboard. The access is given to the shop floor manager. He will be able to see the impact of this CO2 by different KPIs and processes, and we will be able to take the control. And through this seed emission manager, we are aiming to cut down the CO2 emission by 18 million tons. And there are more than 200 initiatives, what I have told already. Out of those 200 initiatives, different in the themes like fuel consumption reduction, circularity, alternative fuels. Today, I would like to take a deep dive into the 4 focus areas, 4 projects, which are like waste plastic injection in blast furnace, COG injection in blast furnace, and also super sinter, which is injection of COG in sinter plants, and also charcoal trials in sinter plant. So let me give a context setting before going to details of the plastic injection. In India, there is almost like 10 million ton plastic is generated in every year. And out of which 60% of the plastic is recycled and 40% of the plastic is creating the pollution. And India is presently operating somewhere around having capacity to produce a 120 million ton steel. And it is very ambitious to produce 350, 400 million ton by 2050. At the present level of 120 million ton capacity of steel production, if we consume this 4 million ton of plastic in our plant, I mean to say in India, that will be around 30 kg plastic injection in blast furnace, 30 kg per ton of hot metal. So that will give us a good benefit.
To study this 30 kg impact in the blast furnace, so we thought we to begin this trial with, we do some trial and check the feasibility. So the objective of this trial is to demonstrate the successful plastic injection by conducting the multiple trials such as various kind of plastics like plastic chips, granules, and we are also working on we have different kind of lances for injecting PCI like single lance, coaxial lance, and with PCI and without PCI. So we have set kind of design of experiment, and we have started working on this. So the main methodology is we are planning to inject in through 2 years. Because of higher hydrogen content, it's a good replacement. We are one-to-one replacement to coal to coke to plastic is one-to-one replacement. And we have conducted the various trial, like first set of trial is with fibrous plastic chips up to 20 kgs. We have taken from our state government, and we have seen some problem with our injection facility because of the fibrous nature of the plastics, and our upper got choked. The second trial, we have planned to use the granules. So this also we have started in one of our medium-sized furnace, around 2,000 meter cube furnace. So initially we have started injecting up to 1 kgs, but it got melted in the lands while we are ramping up to 30 kgs. So we have set the third trial with coaxial lands. So where we injected around 300 kgs. So the melting problem with the single lands is avoided in the coaxial lands. So this first set of trials are like, this is we have did in the upper got choked. Next. The second trial, we purchased from granules. We made the granules and we did the trial. And the results, these lands, the plastic got choked in the lands. So we have gone for the third set of trial. This is the image of third set of trial. So this is injected in 4,000 meter cube blast furnace. So it was successfully injected up to 300 kgs. The plastic size is 3 to 5 millimeter granules plastic we are injected. And the way forward, we are discussing with our state government to identify and segregate the granules. And we are going to make in a larger scale of the usage.
The next lever is COG injection. Next lever is the COG injection in blast furnace. Before going to details, I want to give the context setting of the COG. We have got 3 coke oven plants with capacity of 6.5 million ton and generates around 3,25,000 nm cube per hour gas, COG gas. So presently this gas is being used in reheating furnaces in the downstream mills and all. So in future, as I told already, my colleague also told that RE power we are going to go for the RE power 1000 megawatt. And also we want to go for the electrification of this reheating furnaces. So with that, we want to use this COG gas and inject in the blast furnace. So this slide shows the chemistry of COG gas, what we have in our plant. It is much rich in the hydrogen with 56% and methane of around 25%. The challenge for using this COG gas remain the impurities which we are working on.
So while carry out this COG, we just did a understanding of the CO2 impact. So COG directly, like we can inject in the tuyeres, or we can see the impact of making syngas and inject in the shaft. So we have selected two furnace, like medium size furnace 2000 meter cube and 5500 meter cube capacity of furnace. So in small furnace or medium size furnace, this COG or syngas impact is very, very less because of efficiency factor. Well, in the large furnaces, while adding this coke oven gas, we are getting in 2 years, we are getting a good benefit. Like we are getting syngas around 66 kgs in large furnaces, whereas we can increase the syngas in smaller furnace up to 450 meter cube. We are getting around 99 kgs benefit in the CO2. The major impact is like scope 1, scope 2. Because of higher grid emission factor of COG to power factor, we are getting a lesser benefit of COG injection in the blast furnace. So the exporting COG as a source of energy versus consuming the feedstock in the blast furnace is more beneficial when we get the grid intensity factor of 0.64, whereas currently we are at 0.8. So in future, this is going to be after converting into RE, it will going to be a breakthrough technology for CO2 reduction.
Yeah, coming to the super sinter, what we have taken trials in studied about the super sinter in our plant. So as I told, we have got COG gas. We want to inject in sinter making also. We want to take that gas into the hood and put it in the sinter plant. So this is about the sorry. Yeah, this is about the charcoal, what we are used in sinter plant. Charcoal, we have taken multiple trials. If you see, we have replaced this charcoal with the solid fuel, that is coke breeze. The replacement, we have put a trials of around 22%, 45, 65, 85%. We could see there is an improvement when we add this charcoal at 20, 25%. Over and above, it will give a negative impact. So if you see, the tumbler is, sintering time has come down at 25%. Also, the tumbler index has improved. So in overall benefit, 8% improvement in productivity and 1.4% improvement in the tumbler index and 15 kg CO2 reduction. And also it has improved the SOx and NOx levels. So this is about the COG injection. There is a misplacement of the slides, it seems, sorry for that. And when we injected this COG in the sinter plant, we could see the difference in combustion temperature of fuel gas and coke breeze enabled the sustaining the favorable temperature of 1200 to 1400 degrees Celsius for longer duration, which helped in increasing the bed height and reducing the coke breeze addition in the sinter plant, which in turn helped in increasing the productivity. So with this, we are able to say that 2.5 kg per ton of coke is reduced, and also there is 7 to 8 kg CO2 reduction for every ton of per ton of crude steel. So this is the last summary slide, what JSW Steel is working on decarbonization. Before the total summary, we are going to put it in 3 phases: 2030, 30 to 50, and 50 to 70. If you see 2030, the major enablers are like, presently JSW Steel is having a beneficiation capacity of 40%. We are having 20 million ton capacity iron ore beneficiation plant. Further, from present level of 40%, we are going to 84%. We are installing new beneficiation plant and we'll be washing iron ore. So we are going for 84% of beneficiation of iron ore, what we are going to procure. And also apart from that, in future, reduction in coke rate is going to come through COG injection, and there are many other things which we are doing it, and reducing the utilization and increasing PCI. increasing usage of RE. Total JSW Steel, maybe at 50 million ton capacity, we required 4 gigawatt of power. For 4 gigawatt of power, we have got a roadmap plan of generating around 2 gigawatt RTC power, RE power. And apart from that, we are exploring the technology like CCUS and increasing the scrap usage. Presently, we are using around 13-14% of scraps. So coming days, we want to charge up to 22-24% of scraps in our steel making. And creation of carbon sinks and efficient logistics through pipe conveyors. Thank you.
We have some minutes for questions from the audience. Could you wait here? We have one question there. The lady.
Yeah.
Anybody can help with the microphone, please? Now it's coming.
Thank you for your presentation. Well, I want to ask about the emission from injecting the plastic. Was there any complaint from the environmental regulator regarding that? Because usually when you're going to inject plastic, there will be another emissions, right? Okay, so was there any concern with regard to that?
Environment. As such, we have not faced any environmental issues.
Like NOx, SOx, nothing?
No. Apart from this, we are also putting the plastic in our coke oven. Already, in last couple of years, we have added around 450 tons of plastic in coke oven. And this is the first time we have taken the trial in blast furnace. So we want to further add this plastic into blast furnace. We have not seen any results or negative impacts on the SOx and NOx as of now.
Thank you. Another question from the audience? There.
Still, I will say it was really a wonderful presentation. Congratulations once again.
Thank you.
My question is especially related with R&D. Actually, with respect to your topic, what presently R&D is doing in field of especially alternate carbon sources?
R&D is mainly focusing on a couple of things. Mainly one is usage of this charcoal in sinter plant. That is one. And also we have got, we are also going through the beneficiation. Presently, the iron ore what we are getting is of very low grade and the tailings are very high. So R&D is working on reusing those tails and using it in pellet making and sinter making. This is second part where R&D is working. And third part, R&D is working on CCUS. That is one major thing. These are the major activities which are going in R&D.
Thank you.
Okay. We thank our colleagues from JSW.
Thank you, sir. Thank you very
Very
much.
nice presentation. Thank you. Next presentation will be Mr. Sanjeev Manocha. He's Global Director for Business Development in LanzaTech. The title of his presentation is Decarbonising through LanzaTech Technology at Scale. Thank you.
Yeah, thank you. Good afternoon, everyone. What a pleasure to be here in World Steel Association. So first of all, thank you, World Steel Association. Thank you, ArcelorMittal. Thank you, all our partners, including Primetals and everyone. Thank you for that. So let's talk about LanzaTech. Hold your breath for a minute. I'm going to talk something very innovative. You might have heard about it, but we've done something amazing over the last 15 years. 15 years back, no one would have believed that this can happen. But 15 years later, we are a public limited company, or we listed on NASDAQ from a startup in 2005. We have a huge financial backup coming from major financiers like Brookfield Capital, in Europe and US, Al Align in Saudi Arabia. So I think that we have a very strong, promising future going forward. So I'll just take you through the journey, what we have done so far. So thank you for bearing with me. I'll also appreciate if there are any questions if you have during the process. Sorry, how does it operate? Okay. Thank you, thank you. This one? Yeah, sorry, we have disclaimer as a public listed company, so we are just newly listed public company in 2023. I'll just move on quickly. We spoke a lot about scope 1, scope 2, scope 3 emissions. We all realize that energy, power, can be carbon free. We don't have to use our waste gases from the steel industry to produce power, because at some point, we will get green energy in place. So we believe that power, wherever we use, wherever we can use in the future, has to be carbon free. However, fuels need carbon. When I say fuels, I'm not talking about the road transport fuels, I'm talking about the aviation fuel, an example, where we don't have the technology yet to use hydrogen-based sort of batteries or hydrogen-based fuels to fly airplanes today, but we need carbon basically for the fuels as of today. So sustainable aviation fuel is just one example. Chemicals. I think sometime we, in the steel industry, I come from steel industry background, we do not understand or appreciate other industries' bottlenecks or what they're doing. Believe me or not, as much as steel is essential for all of us, carbon is more essential for all of us to survive on this planet. Carbon is embedded everywhere. We wear our clothes, we sit on the chairs, everywhere there is a carbon. Nothing is possible on this planet without carbon, and we can't make steel even without carbon. As in the previous presentation, someone said, steel is an alloy of iron and carbon, so we need carbon everywhere. And chemicals definitely need a lot of carbon. What we have done over the period of time, we just come from a very basic concept back in New Zealand in 2005, developed the technology and taken it to the commercial level, and so pleased to announce that we have commercialized the technology with ArcelorMittal. We produced at the commercial scale our ethanol last month. So the process is very simple. As you can see, the gases, industrial off gases from steel plant or anywhere, we are interested in 3 molecules, just 3 molecules, carbon monoxide, carbon dioxide, and hydrogen, just 3 molecules. As long as those 3 molecules are present in the gases, and we can do that magic with those gases. Industrial off gases with some CO, CO2, and H2 goes through the compression. We have to do a small cleanup, not a major cleanup like other processes. And then it goes to the biofermentation, to the bioreactors. And the bioreactors, the bacteria, our patented bacteria, does the job. It's all biological process. The bacteria eats carbon from carbon monoxide. It takes energy from hydrogen and also from carbon monoxide. And it also takes carbon from carbon dioxide. So it's just a bit complex. I'll explain in a minute. So it produces ethanol. If it is only carbon monoxide gases, like from the blast furnace, we don't need any hydrogen. So we can just take carbon monoxide to produce ethanol, which is C2H5OH. So we take carbon and we take hydrogen from the water with water gas shift reaction. So we make ethanol out of it. It's all biological process. So ethanol is produced, it is separated, 99.999% purity, and stored and used for various applications. Before going to the applications, just wanted to show that industrial off gases where we started, we expanded to municipal solid waste. Anywhere around the continent, wherever you can go, if there is any municipal solid waste, that can be recycled back through the gasification process and convert and produce ethanol and other products. So direct air capture, which is a distant dream, maybe in 2050, 2060s, we have proven at the pilot scale that this technology also works with direct air capture, carbon dioxide from the atmosphere. So what we do with the ethanol? Ethanol is just a building block for us. Ethanol is not the final product, and we completely understand and appreciate for the steel industry pain that you don't want to go into chemical industry. So we are here to help on that front. if you produce ethanol, when you produce ethanol, that ethanol is very low carbon footprint as compared to fossil fuel ethanol. It's very, very low carbon footprint. Once an ethanol gets converted into ethylene, it opens the entire world for you. With ethylene, you can make fuels. With ethylene, you can go into chemicals. With ethylene, you can do whatever the daily things what we do in our life. So fuels, proteins, and materials. Just talking about the protein. So protein is a byproduct from our process. It is not the main product. So the biocatalyst over a period of time, it gets consumed. So about 5–10%, it comes out as a protein-rich material. So in a sense, what we are doing is we are taking the carbon from the plant, from the industrial processes, taking it back into the process, and using that and producing those products which are value to you guys, to all of us, and then taking those materials back and creating a circular carbon economy in a sense. So what are the carbon is available on the planet? We are not encouraging to bring carbon from the fossil sector. We are not encouraging that, not for a single minute. What we are saying is that what are the carbon is available on the planet, let's recycle that carbon as much as we can. So the journey for LanzaTech, I said before, 2005 startup, but we have built up few plants at the commercial scale already. 2018 was the first plant we built up at the commercial scale in China. As you can see that this is certified ethanol with ISCC plus and also RSB certified this ethanol, which means very high grade ethanol can be used into aviation sector, chemical sector. And then we went on to 2021, 2022, and 2023. We kept on commissioning plants one after another. So we had 4 plants until this year, which were commissioned at the commercial scale, and we are using ethanol for various applications. 2023 was very, very specifically very important year for us, very important year for 2 projects. One project was with Indian Oil Corporation, which was just a very unique project. They had their emissions, which were very rich in CO2 content, and they had emissions also which had high hydrogen content, which was being vented into the planet atmosphere. So we tried to bring those together, 2 molecules, and started producing ethanol, creating value for the client. The second one, of course, with ArcelorMittal, Belgium, at Ghent. So I have a colleague from ArcelorMittal, Belgium. So what we did over there, we set up the plant, we take the blast furnace gases, part of the blast furnace gases, and use those blast furnace gases to produce ethanol. And last month, as I said before, we run at the commercial scale, and we produce hundreds of tons, and next year we'll be producing thousands of tons from this plant. And most of you are welcome to visit Steel and All, and I'm sure ArcelorMittal will help us if you would like to visit Steel and All in Ghent some point. I would like to take you through the journey. Thank you again to ArcelorMittal for sharing these slides with us. Just a journey, quick journey through ArcelorMittal commissioning, that how it happened. And please appreciate that during this period, we also had COVID, and we had labor shortages and all those stuff happening during that period. So it took a little bit longer time than what we anticipated. So 2019 was the ground prepared. 2020, this is how we see it, Steel and All. And if you go further, 2021, and this is how it looks like today. So this is the plant which is producing ethanol as on today. I think the World Steel Association members were there actually at Steel and All, correct me, I think about a few months back, yeah. So as you can see, the orange pipeline is for the gas feed, the gas which comes from the blast furnace diverted to LanzaTech, and part of the gases go back to the power plant again. So we don't waste any energy. We take what are the best we can take. We take all the carbon, whatever we can, energy, and rest of the gases are given back to the power plant again. So it's quite eco-friendly system what we have built for ArcelorMittal. Oh, I'm sorry. I was too quick. So just talking what ethanol as a building block, what we have produced so far. So these are the products as you see on this slide, and you can see the brands at the bottom of the slide. Coty is Gucci perfume actually, so most of us we use perfume, Gucci perfume. If you come to London, if you go to New York, you'll find Gucci perfume made from ethanol coming out of LanzaTech process. So they have taken, and there's a tag actually which has a high premium of course, that this is not from the fossil-based carbon, this is from the recycled carbon. Zara has made dresses using our ethanol. And so on. There are a number of brands, you can name it. So starting from clothes and perfumes and packaging, and also if you talk about aviation fuel, and also shoe soles. ON company, they used ethanol to produce shoe soles, actually using our ethanol. This is about sustainable aviation fuel. So ethanol, one building block is to go into the chemical sector, where you create huge value for the clients, for you. And the second thing is about the sustainable aviation fuel. You can take that ethanol, convert it to ethanol, and produce sustainable aviation fuel. LanzaTech was, again, the initial inventor of this technology. So back in 2019, we spun out that company because it's totally a separate business. So that company was spun out as LanzaJet. So we have LanzaJet producing sustainable aviation fuel now. So we have about 7 plants coming up at the commercial scale producing sustainable aviation fuel from ethanol. As you can see on the right-hand side, the carbon footprint from the sustainable aviation fuel is rather negative. If you compare with the fossil equivalent, we have 89 grams of CO2, and we are talking about 14 with LanzaTech process with biogas feedstock, and with renewable energy, we are talking about the negative carbon footprint actually on the planet. Another important thing, we completely understand and appreciate that the technology, whatever we are doing in the steel industry, will evolve over a period of time. There will be new technologies coming up. It's not that we are trying to promote blast furnace. What we are trying to say here is use the technology, what is commercially proven today, and start creating value and start helping planet to reduce the carbon footprint. So our technology is very much customized. It's more of, I would say, modular technology. So what we can do is that as on today, we have a technology where we produce ethanol by using one type of bacteria. But tomorrow, we have already proven the technology at a pilot scale and also at some demo scale plants. We can produce isopropanol as another chemical, acetone as another chemical, MEG. So we will use the same reactor, same equipment, everything remains same, no change at all. Only thing you change is the feedstock. So you change the feedstock, you change the bacteria, and you get the material, what you really want to produce. So we are working, LanzaTech is a crazy company. We have lots of PhDs, doctors working every day and night. So we have a number of molecules which we are developing in our process, and we are expecting that we will be developing some more molecules in the near future to help the chemical industry. So if I talk about iron and steel decarbonization, where we fit actually as LanzaTech, IEA report in 2023 clearly states that CCUS is going to play an important role. They did not differentiate that how much CCS and how much CCU. It's about 37% is CCUS occupied, equipped steel by 2050. We have a number of options, and we all are completely confused with those options, honestly. And we also know that where is the commercial value in those options? We are just struggling as in trying to make a decision that which direction we should go. Should we go for DRI electric arc furnace? There are many plus. There are many minus also with DRI electric arc furnace. If you think about going into carbon capture sequestration, this is a solution, but this is a cost avoidance. So if you talk about the emerging technologies, we are at very low TRL right now. Probably we'll have to wait for another 5, 10, 20, 50. We don't know how long will it take to get those technologies. But then carbon capture utilization, what we have developed as LanzaTech, so it is already proven at a commercial scale, which can be implemented if you order today within the next 2 years. You will start helping planet and also creating value for yourself. So what we see that as LanzaTech on its own, we see that we can help the industry right now. This is just a schematic roadmap that we can help. If you bring in LanzaTech technology together with your blast furnace as an example, you cut down your footprint by about 20-25% depending on the gas composition. Even with the DRI, if your top gas is having CO or even CO2 with hydrogen, then also you can cut down your carbon footprint. Over a period of time, when the hydrogen becomes available, either through direct use of hydrogen in the steel making and indirect use of hydrogen in the LanzaTech process, so you can go back to nearly zero carbon footprint. And if you invest in this technology today, the technology never gets redundant. It will still be there with the steel making, and in the worst case, with the municipal solid waste, an example. So this is another schematic, a case study which we did for a client. What happens if the client goes from blast furnace to DRI or some other process, and they don't have any CO anymore. So just to say that blast furnace gases are CO-rich gases, lean, but okay, still comparatively CO-rich gases. So we take just CO, we don't add any hydrogen to capture carbon initially. So we only capture a percentage of carbon because of the stoichiometrically, we can only capture part of the carbon, not enough energy in the process. So we capture about 20-25% carbon from the just lean blast furnace gases. When the hydrogen becomes available, we reduce the blast furnace gases volume, we increase hydrogen, we still keep on producing the same amount of ethanol. And over a period of time, we also increase the carbon capture to more than 90% in ethanol. We are limited, of course. It's again, like we have some limitations because of the stoichiometric. So how much energy is available, how much carbon is available in the process. So depending on the gas composition, it varies CO-rich gases. So we have carbon capture efficiency about 33% theoretically. The moment we start adding hydrogen, we can gradually take it to 100% carbon capture efficiency. So we have commercially proven at all the scales with CO plus H2, and also CO2 plus CO plus H2. But this is at the pilot scale where we are at H2 plus CO2 right now. So just in a simplified way, just to show you that how it looks like today, this is a typical steel plant. We take the gases, we either flare it, very rarely, but sometimes we use it for the power plant or some other applications. What LanzaTech does is take out the gases from the power plant, bring it to the LanzaTech process, improve your energy efficiency with those gases, and give you a chance to produce power, which should be fossil-free power with no carbon footprint, green power, and then produce these products which will add value much more than what you get from the power plant right now. So just on the last slide, the new carbon economy, what we believe and what we think is probably need endorsement from you all, that carbon economy has to be like a circular carbon economy. So wherever it is coming from the waste, there is a value in the waste that is coming from the industrial off emissions. Take those gases, go through the LanzaTech process, and produce the products, and take it back again to produce a circular carbon economy. So we believe that the world has enough carbon for sure. We don't need to dig any more carbon from underground. Just leave it there. Let the planet survive and thrive, and we can create value. What we see as a waste, we can create value from that process. Thank you.
Thank you, Mr. Manocha. Very interesting presentation. We have some time for questions. We have one there.
Thank you for presentation. I'm Tomoyuki Okida from JFE Steel Corporation. Please tell me about the cleaning up method before fermentation and the separation method after fermentation.
Sorry, I could not hear very well. Can you, sorry, repeat your question again? Sorry, can you please repeat your question once more? Sorry, I did not get it.
To repeat the question.
Sorry. Please tell me about cleaning up method before fermentation and the separation method after fermentation.
So if I understood correctly, so your question is more about the process itself for the LanzaTech. Am I right? And I'll just go back to my previous slide. 1 second, please. So your question is for
yes,
this slide, right? So you would like me to elaborate more on the cleanup process, yeah?
Cleanup process and separation process.
Yeah, sure, absolutely. Thank you for that. So for the cleanup process, our technology was initially developed at the pilot scale in New Zealand with BHP Steel. So the bacteria was engineered for the steel mill off gases. So we don't have to have a huge cleanup except for certain processes where you emit some of the gases which could potentially kill live bacteria, because bacteria is ultimately live. The only thing which we do not encourage to go into a process is because anaerobic bacteria, oxygen has to be killed before the gases go into our process. So that is the first thing that we have to look. And further to that, we need to see also if there is any poisonous gases which could kill bacteria. But generally, we love sulfur. Our bacteria love sulfur. So there is no problem with sulfur. Our bacteria loves all other gases, nitrogen and everything. There is no problem at all. Its only thing is if you use some raw materials which could create some poisonous gases which can kill the bacteria, we have to filter those gases for sure. And to elaborate on the separation process, so we have the distillation process. With the distillation process, we separate out the water and the ethanol. And ethanol, of course, is purified and it goes for the further processing.
Oh, thank you very much.
Thank you.
Another question. I hope now it's better. Thank you for your presentation. Very nice presentation. I just wanted to ask you, in your point of view, what do we need in order to incentivize the utilization market, in order to grow the market to large enough in order to consume the more than 3 billion tons that we produce CO2 within the steel industry today? What do we need to incentivize even more the market utilization for the CO2?
So, sorry, if you mean incentivization from the policy side or from the customer side?
Both sides.
I think, yeah, as on today, CCU, let's be very honest, for some reason, CCU has not got enough sort of importance within the policy sector itself. CCS and hydrogen has become big, I'm sorry to use the word hype. So CCU has taken a little bit a backward step. If you go back 5 years, probably, and then there people were talking about CCS and CCU. Now CCU is coming under umbrella of CCS, but there are two totally different technologies at all. I think there has to be some recognition from the policy makers that there is carbon we need. We can't go without carbon on this planet, right? So they have to appreciate and they need to know that the carbon can be a circular carbon economy rather than producing carbon from the fossil sources, right? So that's the one thing from the policy side. And also from the steel industry perspective, we think that we have a strong IRR, internal rate of return. We can do the return on investment basically for your project, depending on the gas composition. We can capture all the carbon as long as there is enough energy available. But again, we depend also on the hydrogen at some point. So when we can use all the energy, whatever is available in the gases, we need more hydrogen to go into the process. So we are fully aligned that the policymakers have to work on the hydrogen for direct sort of steel making reduction, but also for the indirect carbon capture actually through the process. So I think we are definitely dependent on the policymakers to incentivize the CCU sector in totality. So unfortunately, we are the only one, as on today, the leading one for the CCU sector. We don't have many companies yet. We are definitely encouraging that competition should come up in the CCU sector, so we all together can go and convince the policymakers. I'm sorry for the long answer, but probably I answered your question. Thank you.
One last question. Okay, sure.
Yes, first of all, thank you, Mr. Sanjeev, for the very good presentation. You have mentioned about the power generation. So can you explain more? Do you mean capture the off-take gas, produce ethanol, then use it for power generation, or directly capture the off-gas and use it for power generation?
Thank you for your question. Sorry, I was probably not clear actually in my presentation, so my apologies for that. So we take the gases directly from the blast furnace or from the DRI process or from the BOF process. We take the gases directly. We take that carbon without any external power. We don't need any external power actually, and we don't produce power. We take that carbon and energy, which is chemical energy, through hydrogen molecule or CO molecule. So that energy is sufficient enough for us basically to produce ethanol. So we produce ethanol as a molecule. And the slide what I showed before was that as in today, conventionally steel plants are making power using fossil gases to make power. So we are saying that we are better off making ethanol rather than making power because you have better energy efficiency of the ethanol as compared to the power, conventional power.
Thank you very much.
Thank you.
The very last one.
Hi, Sanjeev. It's a very good presentation. Sujan from Tata Steel. I would like to ask one question. In this whole process or the future, as the ethanol is considered as a CCUS project or intermediate project for the SAF, so you require hydrogen. Am I right?
Sorry.
To produce ethanol or SAF, you require hydrogen to extent.
So depending on the gas composition, right?
Considering the blast furnace
gases, we don't need hydrogen.
Okay.
We can take CO molecule.
Okay.
From that CO molecule, we can produce ethanol because there will be some water gas shift reaction happening in the water itself. So we do the water gas shift reactant. And then we take the hydrogen from that reaction to produce ethanol, C2H5OH.
Okay.
We take the hydrogen from there. But the efficiency of the carbon capture rate is limited because we are depending on the CO composition, right? Or the hydrogen, if there is some hydrogen available. But if you enrich those gases with hydrogen, external hydrogen, then we can increase carbon capture rate to 94% depending on the amount of hydrogen available. So minimum 20-25%, maximum 94%.
In that long run, how do you see, because hydrogen can be used in CDA, carbon direct avoidance in blast furnace or DRI, as compared to CCU. So how do you see in the long run in your roadmap that is it compete with the CDA?
I think it lot depends on the economic value what we create for our customers, right? If you tomorrow, depending on the market situation, so if I take a couple of years back when we were running into the COVID situation, acetone prices, we are also producing acetone, right, by the way. So acetone prices have gone skyrocket high, right? So acetone could be a huge value for the steel plant that time to rather than using, I'm just using hypothetical situation, rather than using hydrogen to produce steel where there was no premium available, you could produce acetone using that hydrogen and it could add a lot of premium. So we are giving a flexible arm to steel producers that you can use hydrogen in the direct steel production if you have good premium. At some point, we know that green premium will go away, so you won't get the green premium. Everyone is producing green steel, there won't be any green premium. Then if you produce ethanol with very low carbon footprint, it could still fetch a premium. So we see that in 2050 also, there might be a strong business case of using hydrogen in producing ethanol through indirect sort of carbon capture rather than sort of direct reduction of carbon direct avoidance, if you want to call it, right?
Thank you. Excited to see your future technology.
Thank you very much. Thank you.
Thank you, Mr. Manocha.
Thank you. Thank you very much.
Thank you very much.
Thank you.
Next presentation will be given by Dr. Yusuke Kashihara. He is Senior Researcher for Ironmaking Research Department at JFE Steel Corporation in Japan. And the title of his presentation is Combining Carbon Recycling Technology.
Thank you, Chairman, for my introduction. My name is Yusuke KASHIHARA from JFE Steel Corporation in Japan. I'm in charge of research and development of blast furnace process for reduction of CO2 emission. Today, my presentation title is Innovative Blast Furnace Process aimed at reducing CO2 emissions by combining carbon recycling technology. We call this blast furnace is carbon recycling blast furnace. This is new blast furnace process. Today's topics is shown here. First, I talk about the background. Next, I talk about concept of carbon recycling blast furnace. Then, I'll talk about evaluation of reduction of CO2 emissions by simulation model. Finally, I'll talk about conclusions. Firstly, I talk about background. This slide shows the current status of CO2 emissions in Japan. Reducing the amount of CO2 emissions is an urgent issue in Japan, in Japanese iron and steel industry. In particular, it is important and impactful to reduce CO2 emissions from the blast furnace process. These figures show the amount of CO2 emissions. The ratio of CO2 emission from iron and steel industry is about 14% in total emission in Japan. The ratio of CO2 emission from blast furnace is about 54% in total emission in iron and steel industry. So, reduction of CO2 emission from blast furnace is very impactful. To reduce the CO2 emission from iron and steel industry, blast furnace may disappear. However, the Japanese steel industry will use blast furnace continuously. This red line shows production of pig iron. According to this graph, pig iron production is expected to remain at roughly current levels at the end of this century. So the way to utilize the blast furnace process is also investigating for utilization of existing facilities and price competitiveness. This slide shows the JFE Steel's transition to low carbon processes. In JFE Steel, to achieve carbon neutrality, the deployment of the most optimized configuration of green steel making processes is investigated like this figure. One is a blast furnace, one is a direct reduction of hydrogen, and electric arc furnace. As one of these configurations, we are developing this carbon recycling blast furnace. Today's topics. Next second topic is concept of carbon recycling blast furnace. This slide shows the concept of carbon recycling blast furnace. The aim of the carbon recycling blast furnace is to achieve carbon neutrality by repeatedly reusing carbon. This is achieved by converting the CO2 generated in the blast furnace process to methane by methanation using green hydrogen. The methane is replaced to coal as reductant. This left side diagram shows the concept of carbon recycling blast furnace. As same as conventional blast furnace, sintered ore and coke are charged from the top of blast furnace, and oxygen-containing gas is blown from the tuya, and hot metal and slag are removed from the tapping hole. The major difference from a conventional blast furnace is that carbon is recycled by using methane synthesized from CO2 in exhaust gas from blast furnace and green hydrogen. The aim is to enhance CO2 reduction by converting hydrogen to carbon neutral methane. The reason for converting hydrogen to methane is that hydrogen does not react in front of the tuya and does not generate heat. However, methane reacts with oxygen in front of the tuya and generates heat. It is a good point. This slide shows the characteristics of carbon recycling blast furnace. Combining carbon recycling blast blast furnace with carbon dioxide capture, utilization, and storage. It's called CCUS. It enables steel works to recycle CO2, thereby lead to net zero carbon emissions. Carbon recycling blast furnace can produce same scale iron and use same grade raw materials and produce same high grade steels as a conventional blast furnace, we think. Next topic is evaluation of reduction of CO2 emission by simulation model. This slide shows the evaluation method by simulation model. The potential amount of CO2 emissions reduction in blast furnace process using the carbon recycling technology was studied with a list diagram. The list diagram is a heat and mass balance simulation model of the blast furnace, like our left side figure. Next, I explain about the evaluation method and consumption, as shown in last slide, this slide. Blast furnace operation, considering operational constraints, was evaluated. In this study, operational constraints is theoretical flame temperature in front of the tuya of the blast furnace and furnace top gas temperature. Blast temperature assuming mixing of hot air and room temperature oxygen was calculated. CO2 emissions were calculated from carbon consumption in the blast furnace. Carbon of carbon neutral methane gas and carbon for preheating gas injection is not counted because both carbon circulate in this system. This slide shows the calculation conditions. The optimum operating mode was investigated in consideration of the operable range. The injection amount of carbon neutral methane and the oxygen concentration in blast are changed, and operational change is predicted by list model. This slide shows the calculation results about theoretical flame temperature. This slide shows the calculation results about flame temperature in front of the tuya of blast furnace. The operation condition to satisfy the heat and mass balance by changing carbon neutral methane rate and oxygen concentration in blast was calculated. TFT decreases due to increase in carbon neutral methane injection rate, and TFT increases due to increase in oxygen concentration in blast. The upper limit of TFT was set at 2,300 degrees Celsius, and lower limits of TFT were set at 2,000 degrees Celsius in this calculation. It is decided based on blast furnace operation result, actual blast furnace operation result. This slide shows the calculation result about the top gas temperature of blast furnace. TGT increased due to increase in carbon neutral methane injection rate because gas volume through blast furnace increases. And TGT decreased due to increase in oxygen concentration because gas volume through blast furnace decreases. It is necessary to maintain TGT by using SGI below 100 degrees Celsius. However, by using SGI, lower limit of TGT can be avoided by using SGI. This slide shows the calculation results about CO2 emission reduction ratio. Carbon consumption reduction ratio increases due to increase in methane injection rates. High concentration and using SGI are required to increase carbon consumption reduction ratio. Maximum CO2 reduction ratio was obtained under conditions of oxygen 100% and increase in methane injection rate up to the TFT lower limits. In the red area of upper part of this figure, maximum carbon consumption reduction area. In this area, CO2 emission reduction ratio is more than 30%. This slide shows the change in carbon consumption balance. In the carbon recycling blast furnace, carbon consumption by direct reduction decreased greatly. The amount of consumption reaction in front of the tuyer is high, but a part of the carbon of the combustion reaction is the carbon neutral methane carbon. So the amount of the coke consumption in front of the tuyer is approximately same. This slide shows the change in heat balance. In the carbon recycling blast furnace, the amount of heat necessary for reduction reaction is small due to the small amount of direct reduction. This direct reduction is a large endothermic reaction. Therefore, the heat demand is reduced. And sensible heat by hot blast is reduced, but increase in heat supply by combustion reaction of coke is suppressed because a part of the heat is supplied by combustion reaction in front of tuyer of carbon neutral methane. Finally, I show the conclusion. A reduction of CO2 emission by the carbon recycling blast furnace was studied using the least diagram approach, and the following knowledge was obtained. Use of carbon neutral methane reduced the CO2 emissions of the blast furnace by the decrease in the amount of direct reduction and supply of heat by reduction with oxygen in front of the tuyer. It is possible to reduce CO2 emissions more than 30% at the maximum by using carbon neutral methane in the blast furnace. In maximizing carbon neutral methane injection, oxygen blowing and preheat gas injection from the upper part level are effective. Thank you for your kind attention.
Thank you, Dr. Kashihara.
Thank you.
For a very good presentation. Are there questions? There is one here and another there. One there also.
Thank you very much for your nice presentation. Actually, my question is, according to the theoretical examination using your race diagram, what factor contribute to more than 30% reduction in CO2 emission in blast furnace, employing carbon recycling technology compared to the conventional blast furnace?
Sorry, pardon. Sorry, one more, please.
My question was that which factor was the most highlighted factor while you were studying in risk diagram, which contribute to your CO2 emission?
CO2 reduction.
Could you repeat it, please? Did you understand? What is the fact that contributes more to the CO2 reduction in your proposal? The main variables. Main variables for the process. In the emissions.
Main process.
Yes. What is the, let's say, what is the variable you can optimize to improve the efficiency of the process? What is the main variable that defines the CO2 emission?
This carbon recycling.
Yeah.
Main process is carbon neutral methane injection technology. By using methane injection, we can achieve great large amount of CO2 emission. But to inject a large amount of methane gas, oxygen concentration in blast is very high, and we are promote finally we are thinking the pure oxygen at room temperature is best condition. And more technology is shaft gas injection. It is needed to avoid the lower top gas temperature, decrease the low top gas temperature, avoid the decrease in top gas temperature. These three technologies is composed this new blast furnace technology.
Thank you. Second question, please. No? There was another here. Yes, there.
So what results you have shown, it's based on the risk diagram, heat and material balance simulation. You have did the simulation and the potential is around 30% CO2 reduction. What is the next plan? Are you going to demonstrate it pilot scale or then industrial scale? What is the next plan of JFE regarding this methanation and injected in the blast furnace? What is the next plan?
Methanation is necessary. Yes, we in this process, carbon neutral methane is necessary. So, yes. Next plan. Sorry. Next plan is we are investigating the small-scale test plant, small-scale blast furnace test plant under construction, and it is start 2025. We think.
Okay. We have one final question, please.
Thank you. I'm just going to ask a question that's coming online from Mr. Lin, who asks, what is the thermal reserve zone or the iron oxide reducing temperature in your model, your RIST model?
sorry, one more please.
What is the temperature of the oxygen, of the iron reduction zone within your model?
ホットメタルテンペラチャーはオキシジェンテンペラチャー。
Temperature on the iron reduction zone. Temperature on the iron reduction zone.
リダクション、サーマルリザーブゾーンin this calculation, it is it set 800 degrees. Yes.
Thank you. Thank you again, Doctor. We have now time for a coffee break. We will have to be back in the room in 30 minutes, okay? 25 minutes, please.